When a rocket blows up, it's usually not a good day. But that isn't the rocket itself malfunctioning, that's an intentional explosion to protect the general public and prevent an even worse day. This is the job of the Flight Termination System, a phrase often discussed in spaceflight but rarely explained. How does it work? Why is it needed? And is there really a human sitting behind a big button? And not every flight termination system is made equal. Sometimes it's not an explosion at all. Let's dive into why rockets need a termination system in the first place, what different types of systems are used for different types of rockets, and we'll answer once and for all, what is a flight termination system? And no, it's not a magical box full of explosives. Rockets are naturally very powerful. They travel great distances very quickly, meaning that when things go wrong, they can go very wrong. It may seem obvious, but because of this reason, launch operators and regulatory bodies don't just let anyone get up close. There are exclusion zones, hazard areas, and huge amounts of infrastructure in place to ensure the land, sea, and sky is clear of obstacles. That way, if anything were to go wrong, then the giant flying tube of combustible propellant should end its journey in a location far away from populated areas. So why on earth do rockets need a flight termination system in the first place if the places they're flying over are already clear of any people? Well, there are a few reasons why it might be a good idea to end a mission prematurely. The previously mentioned hazard zones are fixed in place. They can't be changed on the fly. Therefore, if a rocket starts to deviate from its intended trajectory for whatever reason, and it looks like it's on track to depart those designated hazard areas, you need to stop that from happening. After the flight termination system kicks in, the rocket can no longer produce thrust and therefore will fall back to Earth on its current trajectory. In the case of an explosive flight termination system, smaller rocket parts may also be more ideal than one large rocket falling back to Earth. The equation for momentum is quite literally multiplying an object's velocity by its mass, so if you divide the mass into hundreds of pieces, then the momentum of all of those smaller pieces will drop by a significant margin, reducing the harm they'll cause if they hit anything. There's another factor to take into account with a flight termination system, which is the state you want the payload to be in when it returns to Earth. If your payload is, say, a super-secret hush-hush spy satellite stuffed to the brim with modern espionage technology that you really don't want your international rivals to get a hold of, then if the rocket does something slightly wrong and parts of the payload could possibly survive, then just turning the whole thing into an expensive fireworks display might not be the worst outcome. If the super-secret satellite is already not going to orbit, you might as well make sure nobody else has any idea how to reconstruct it. But what actually is a flight termination system? Most of the time when we're explaining how it works, the FTS is treated as a magical box capable of just blowing up the rocket whenever deemed necessary. And the reason for that oversimplification is because these systems are incredibly complex. Just think about it. A flight termination system has to be capable of completely terminating the flight with 100% reliability. The rocket itself isn't even that reliable because if it was, it wouldn't need a flight termination system. First of all, to cover the very basics, a flight termination system is a system designed to terminate the flight if things go wrong. It is an independent safety system. It has to be able to operate by itself no matter how its parent rocket is currently behaving. One way to accomplish this is to have an entirely separate power supply. A popular option is to have batteries on board the rocket solely dedicated for all of the FTS systems. This way, even if the vehicle's main electrical supply is lost for any reason, the flight termination system can still run its computers, communicate, and operate if required. A recent example of these FTS batteries making the news was back during the launch campaign for Artemis 1, the first flight of the Space Launch System. That rocket is stacked in the Vehicle Assembly Building at the Kennedy Space Center, where a copious number of gantries and access platforms are available to your heart's desire. Once rolled out to Launch Complex 39B, however, the ability to access all but the base of the rocket and Orion's hatch was non-existent. This caused a little bit of a problem because the Flight Termination System batteries for SLS were only rated to last 20 days from the point of installation and charging. Because of this, NASA had to roll the rocket back to the VAB to retest the batteries and ensure they were up to the task of terminating the big orange rocket if it had to. Thankfully, it didn't, and since, the batteries have been uprated to last 25 days. For Artemis 2 and beyond, NASA also built some contingency access platforms, which allow access for FTS servicing when the rocket is out at the pad. In addition to an independent power source, the Flight Termination System also has an independent communication source, typically via a very high power, one-way, ultra-high frequency radio link. This is critical for if the vehicle loses signal to a ground station and stops downlinking telemetry, because if the range doesn't know where the rocket is accelerating to, they're going to have to terminate the flight. But they've lost connection to the rocket. That's where the ultra-high frequency radio comes in. Essentially, this allows the flight termination command to be shouted at the rocket really, really loud, meaning that it will be heard no matter the distance to the rocket or the rocket's orientation. It's almost like how, even if you're subscribed to the channel, sometimes YouTube doesn't always send you a notification, so it's best to follow us across all your favorite social platforms so you never miss a live stream or video. There's another misconception with a flight termination system, and that's the fact that FTS is not a synonym for blowing up a rocket. I must confess, just a minute ago, I told a bit of a white lie. The core responsibility of a flight termination system isn't to terminate the flight. Its core responsibility is to just terminate thrust. Now, that can be achieved by some sort of explosion, but that's not always the case. It's sort of like how the space shuttle is a rocket, but not every rocket is a space shuttle. A common way to terminate thrust, especially with smaller rockets, is simply to turn off the engines. Yep, it's that simple. In the event that the vehicle is behaving in a way which is, or is about to become, a risk to the public, then the best way to stop the rocket flying in that direction is to just stop the thing which is generating the thrust. There are a couple of recent examples of this exact method being used in flight, one of which is the infamous horizontal departure of Astra's Rocket 3.3 on the LV-6 mission, shortly before T+1 second into flight, but unfortunately after launch commit, one of the 5 Delphin engines on the rocket's first stage failed, leaving just 4 engines running. At the time of the engine failure, the thrust-to-weight ratio wasn't great enough to move vertically. However, the remaining 4 Delphins did have enough control authority to return the vehicle to the vertical axis, where it started to drift upwards as it burned its propellant and therefore its mass reduced. And credit where credit is due to Astra's guidance, navigation and control team, Rocket 3.3 continued flying in a stable manner for 2.5 minutes, but due to the roughly 1/5 reduction in thrust, the vehicle was moving towards the edge of its ascent corridor, the predefined hazard zone which is kept clear of boats, planes and, crucially, people. Because of this, the range, which for this flight was the Pacific Spaceport Complex, terminated the mission, which disabled the 4 remaining engines, leaving the rocket to tumble to a hard splashdown in the Pacific Ocean.
Terminate send.
To this day, Astra co-founder and CEO Chris Kemp maintains that the rocket, quote, fully recovered, and that the termination was a, quote, error made by the government flight safety officer. This is despite the fact that the rocket was at half the expected altitude at the time of the termination. When friend of the show Joe Barnard of BPS Space pointed this out, Kemp simply replied, wrong. Another recent example would be the even shorter maiden flight of ESA Aerospace's Spectrum small launch vehicle. The mission, named Going Full Spectrum, commenced from the spectacular Andøya Space Center in Norway, but unfortunately, it would only just clear the height of Andøya's mountains before things started to go wrong. When the roll maneuver started, the maneuver designed to prepare for pitching the rocket downrange to achieve orbital velocity, the vent valve unintentionally opened and there was a loss of attitude control. We can see this loss of attitude control through the back and forth gimbaling of its 9 Aquila first stage engines. Once it became clear that the rocket was no longer continuing on its expected trajectory, the flight was automatically terminated at approximately T+30 seconds, resulting in all 9 Aquilas shutting down and Spectrum falling to impact the Norwegian Sea in one piece. Until the explosion, of course, which may have also had something to do with the fact that the waters around the launch site are not that deep. Fun fact, NSF was on site to help capture and track these launches on behalf of their respective companies. Cutting the engines works great and all for liquid propulsion, but what if you're using a solid rocket motor? Solids are famous for being impossible to shut off. Once it's lit, it's burning all of its fuel, and unless it's really strapped down at a purpose-built test stand, it's flying. To terminate a solid motor at the command of the Flight Termination System, the casing itself is ripped apart. This means that instead of being directed out of the nozzle, the exhaust burns in all directions, using up the solid propellant much quicker than it would be during controlled flight. You may have heard this explained as unzipping, and that's a great analogy. Just instead of unzipping a jacket, explosives are compromising the motor's casing. An example of a solid rocket flight termination system in action is the ill-fated final flight of the Space Shuttle Challenger, STS-51L, but probably not the part you're thinking of. The breakup of the shuttle was not caused by FTS, it was caused by the failure of the primary and secondary O-ring seals in a joint in the right solid rocket booster. This leaked high pressurized gas which burnt through the strut connecting it to the orange external tank and then the tank itself. This compromised the tank's internal structures, which was followed by an unsurvivable rotation which forced the shuttle into a position where it was destroyed by the supersonic aerodynamic forces. Both of the SRBs actually survived the breakup of the shuttle stack and continued flying, but they were now unguided by the attitude and trajectory control of their mothership, which was destroyed. They continued to fly uncontrollably until the range safety officer triggered their respective flight termination systems, which were activated at T+110 seconds. As I talked about earlier, because these boosters used solid propellant, their cases were unzipped, so to speak, causing them to rapidly use up all of their solid fuel. And finally, it's the big one that's most often associated with a flight termination system, the explosive variety on a liquid rocket. But this form of FTS is also a bit of a common misconception, because while it does trigger an explosion, it doesn't always trigger the explosion, which turns the rocket into an expensive fireworks display. Let's use Starship's Flight Termination System as an example, mainly because, thanks to Starbase's location alongside a public highway, it's allowed our cameras to get up close views of not only the positioning of the FTS boxes, but also the installation of the charges themselves. SpaceX employs the use of C4, which is a common plastic explosive utilizing RDX as its explosive agent. Its texture is similar to that of modeling clay, which may be useful when designing the shape of the Flight Termination System boxes. On both the Super Heavy booster and Starship upper stage, the charges are located directly adjacent to the common dome. This is a tank dome which is common to both the liquid oxygen and liquid methane tanks, or in other words, it's shared by both tanks. It forms the top of the LOX tank and the base of the methane tank. Both of these propellants are of course combustible, and when combusted in a controlled manner via the Raptor engines, they can help push the vehicle into space. However, by triggering the charges positioned right next to the common dome, that dome will be compromised and will fail to keep the oxygen and methane separated. Therefore, they will mix uncontrollably, eventually culminating in combustion and the explosion of the vehicle. Hopefully that explains how, while they do explode, the charges themselves are not the flight-ending explosion. They cause damage to the vehicle, compromising its tank structure, which causes the propellants to uncontrollably mix, and it's the mix of these propellants which causes the rapid disassembly of the rocket. The only example of Starship's Flight Termination System charges being triggered during flight, which we were able to see from our cameras, was the first flight of the full stack back in April 2023. This infamous maiden voyage not only created a concrete tornado at the launch pad, causing debris to be scattered throughout the dunes and our van, but also suffered from a very sketchy Super Heavy booster. There were a number of bangs, fires, and propellant leaks in the aft end, which eventually severed the connection to the primary flight computer, causing loss of control of the vehicle. This loss of control caused the rocket to deviate from its intended trajectory, automatically triggering the explosive flight termination system, but that didn't trigger an explosion. Yeah, Starship was so well built that the charges SpaceX installed into Booster 7 and Ship 24 weren't powerful enough to compromise their respective common domes. While extremely sketchy at the time, a 120-meter tall rocket with its engines firing, spinning out of control with no way to terminate the flight, it does provide us with excellent evidence to the positioning of those charges, because the streaming propellant points to the exact spot of the holes punched in the vehicle. Following a bit more tumbling than SpaceX was expecting when the FTS was triggered, Starship eventually ripped itself apart through a massive fireball just before T+4 minutes. Following this close call, Starship has seen a much beefier amount of C4 installed on subsequent flights, although unfortunately we haven't been able to see it used from our cameras as of the time of publication. Starship V3 could change that, however, considering its design is drastically different than before. But how do you actually know when something is going wrong with the rocket? Of course, many rocket failures are visually spectacular, and even the untrained eye can clearly see that something has gone wrong. But what the rocket is doing visually doesn't always tell the full story. To get an accurate tell on what the rocket is actually doing at any given moment in flight, you need to be tracking the vehicle, and that's easier said than done. To learn more about this, I was fortunate enough to speak to Victor Nancy, a software engineer at the European company GTD. They've been developing and operating tracking solutions for various rockets at the Guiana Space Center in French Guiana, the Esrange Space Center in Sweden, and Space in Norway.
I cannot give you all the details about which parameters are controlled and so on, but I can tell you that it's a mix of telemetry data, And then they use, usually they use radar as well to have independent information of the position of the rockets. If you use only telemetry data, on board, exactly, you have a GPS, usually that gives you some independent information, and you have as well the computers that pilot the rocket that can give you information about the position. In French Guiana, they have more system, more captors, different radars. They have more captors to get more information about the rocket, so that they have more information to make the good decision, you know. For example, when they send, sometimes they send very important space engine like James Webb launch. It was very, very important. You don't want to terminate this flight only if it is really, really dangerous. Because if you terminate it, you lose a very valuable device that takes a lot of money and a lot of time to develop. No? They have different constraints in this kind of spaceport and a smaller spaceport as Andoya that sends smaller satellites.
As I was talking about earlier, reliability and redundancy are really important when it comes to a flight termination system. To accurately track a vehicle, it's best to use a number of different variables from a number of different sources. As Victor was saying, if you're flying an extremely valuable payload like the James Webb Space Telescope, you don't want to accidentally send a termination command because of some inaccurate data. Therefore, both vehicle-based and ground-based assets are used to determine the current trajectory.
Something that is shared from all spaceports is that you will use what they name the impact points. So from the position, in real time, you will compute what's going on. If I stop the engine now, where my rocket will fall down on Earth. So the impact point, it's a ballistic trajectory that you compute. So you can see if now I terminate, where is going to end my rocket. No? So it's very important information from them. So they have to guarantee that at any time they can terminate safely. So if they see that this impact point goes to dangerous an area, hazard zone area, an area they don't want the rocket to fail, they will try to terminate it before. So that's a common information they use on all spaceports, and I think in the US as well. But then there are information based on onboard data as well. I don't know, maybe pressure levels, I don't know. So something you want to check sometimes, for example, is the link with the onboard termination system. You want to be sure that the link between ground system and onboard system is working properly, that the onboard system to terminate is working properly. If you start to see that some parameters are starting to go bad, you might take the decision to destroy it before losing the capability to do it.
Even though the tracking software provides an impact point, that might not always be a representation of where every single component of a vehicle will end up. For example, different materials will descend in a different manner. Carbon fiber is more likely to shatter into tiny pieces, which can be carried by the wind. Metals, on the other hand, are more likely to deform and survive as larger, denser pieces.
And usually they want to use different captors as well, so that they can compare them between each other. You can imagine that one of the captors, if one radar starts to have a failure, it might give you a wrong trajectory. So it might give you wrong information. And from that, you can think, oh, my rocket is dangerous, I have to terminate it. But it's wrong because the captor is failing. So that's why as well, you want to have different captors and a voting system, usually at least 3 captors. So you can confirm. If one captor say it's dangerous, you can check the 2 others. If 2 say it's dangerous, then you terminate, for example.
While this telemetry will provide a much clearer picture of the rocket's current situation for the vast majority of the flight, traditional cameras still have a role to play when determining the vehicle's health.
Sometimes they might be used just at the very beginning, because to verify that the rocket is starting well. If you see that from the beginning the rocket is, instead of going straight up, is like falling and going that way, that you might want to destroy, and maybe with the camera you will see it directly. And from the computer, that takes more time, no? But after that, you don't use camera.
And this ground tracking software works across the various types of flight termination system discussed earlier, whether it be explosive or just shutting off the engines.
From ground, you just send a signal. You send the order. You have to terminate. Then, if it is cutting the engine or an explosion, it's the onboard system. So it's really independent from the ground. The ground system, they are built with very simple interfaces. And so normally you can use the same system for any flight. Can happen because telemetry is different from one flight to the other one. So that's why you need some configuration sometimes to adapt the system to the telemetry of of the rocket you're launching. But normally there are systems that you have, at each campaign you have to reconfigure your system, but it's the same system, same code, same hardware for all the type of launcher.
Let's assume that the software has received data, gone through its verification to ensure it's accurate, and returned that the rocket is deviating from its planned trajectory. It needs to be terminated. But who actually makes that call? Well, to be more accurate, the question is, what actually makes that call? This brings us to the two most discussed variants of flight termination systems, manual and automated. In the case of a manual flight termination system, a human is in the loop. The person in charge, usually called the range safety officer, is quite literally sat at a console with a button, which, if pressed, will terminate the flight.
Usually they have maps, very simplified maps, and then you have some limits. You see the limits that the rocket cannot, the areas where the rocket cannot go, and you will see the position or the impact point. And you will have some safety criteria as well computed by the software, so that will give you red or alarms to tell you, oh, there's something wrong with this criteria, there's something wrong with that criteria. So from this information, altitude, position, impact point, and some safety criteria, you will make your decision. For the flight safety officer, the decision has to be taken very quickly. So he doesn't want to have too many information to compute, to process, because he will not have time to process all that information. So the idea is that the software will try to, that's why there are algorithms that will help him to take fast decision. So what he wants is only see critical information, the simplest as possible, so that you can take as fast as possible a decision to terminate.
If the RSO sees the rocket doing something they don't like based on the information being provided to them, then they will press that button.
Apart from the flight safety officer, at the end the flight safety officer is the last operator, but there are much more operators around, because there are operators that will guarantee that the radar is working well, that the telemetry is going okay, or some operators that will check that, I don't know, vessel traffic is okay, there's no boats on the road, flight traffic. There are much more on this kind of system. There is a lot of operators operating to make sure that everything is working well. And the flight safety officer is, there will be operators as well responsible for the flight termination system as well itself, to be sure that the flight termination system is working properly. And so the flight safety officer is one on all of them. But he is the one that at the end they all work for him, because he's the one who has to take the final decision to terminate.
In fact, we've seen a real-world example of a launch not going ahead because the authority charged with the supervision of air traffic was unable to monitor the range.
This is LD on countdown 1, hold.
For more on that specific scenario, check out this video we made on how a regional power outage scrubbed a SpaceX launch. That SpaceX launch in particular, however, was using an automated flight termination system. As the name implies, this system does not have a human in the loop, and all decisions are made by a computer on board the rocket. This can have some big benefits compared to a traditional system. Before launch, a set of flight rules are uploaded to the AFTS computer, essentially instructing it on when to trigger a termination. For the purposes of explanation, if variable X exceeds limits, trigger the AFTS. And because it's a computer, it's able to make that decision in a fraction of the time it would take a human to come to the same conclusion, both because of the biological limitations on brain power and also the physical limitations in needing to press a button.
At the very beginning, you could have cases where the decision has to be made in less than 1 second to terminate. So in that case, a human being cannot do it. Just the time to go to the button, it's too late. So in that case, you want to use automatic mode.
AFTS also doesn't make use of ground tracking infrastructure. It takes all of its measurements from onboard systems which don't need to be fed or paid. Traditional FTS, on the other hand, requires radars, command transmitters, antennas, amplifiers, telemetry receivers, downrange sites, and of course, personnel. Because the automated variant is running on board the vehicle, it can also be used when out of sight of a ground tracking station. This is actually a really useful factor. You may know that Rocket Lab's first launch of Electron back in 2017 ended in failure, but it wasn't the rocket's fault. Instead, a ground-based tracking station lost telemetry from the vehicle, causing the FTS to be activated. If it was an automated FTS, it could have made it to orbit. Today, Electron flies with a fully autonomous flight termination system. The opposite can be said for the third flight of Japanese company SpaceOne's Kairos rocket, however. A similar size to Electron, this vehicle utilizes 3 solid propellant stages and a liquid upper stage. It's had a troubled start to life, with 3 consecutive failures as of publication. Although the investigation into the third failure is still ongoing, initial reports suggest it could have been caused by the automated flight termination system being inadvertently triggered. Had this been a manual FTS, then maybe the vehicle could have delivered its customer payloads into orbit. To prevent failures like what happened to Kairos, these automated systems require rigorous certification and testing because the software is complex, but for launch providers like SpaceX, this is easily made up for the fact that it can support much higher launch rates. Because it uses onboard systems, it doesn't have to rely as much on assets provided by the range, meaning each launch is less of a burden, so they can fly more often. Another item to note is reusable launch vehicles like Falcon 9 will have multiple stages in controlled flight simultaneously. For Falcon Heavy, it's up to 4 different stages all flying independently after staging. An automated system on each of these stages only has to be concerned with the stage it's flying on, compared to a human range safety officer trying to keep tabs on 4 flying objects at the same time. So now you know why rockets need a flight termination system, what a flight termination system actually is, and how we trigger a flight termination system. I think it's time we take a look at some historic examples of these actually in use, don't you? We're starting off in French Guiana, where in 1996 the European Ariane 5 made its debut from the Guiana Space Center, igniting its single Vulcan 1 engine and twin AEP P238 solid rocket boosters. The vehicle leapt off Ariane Launch Complex 3 with an initial flight which looked to be going as expected. However, something was happening with the rocket's onboard inertial navigation system. This uses a series of motion and rotation sensors to determine the vehicle's current position, orientation, and velocity. Now, for whatever reason, when designing the Ariane 5, the code within the INS was literally reused from its predecessor, the Ariane 4, a much weaker launch vehicle in comparison, capable of delivering half the payload to orbit of the Ariane 5. This new, much more powerful vehicle accelerated horizontally much faster than the Ariane 4, meaning the INS was receiving a value much higher than it was designed to compute, so high in fact that it caused the value to overflow. The number was literally too big to handle. This caused a hardware exception which stopped both INS modules, which, to oversimplify, confused the flight computer to the degree that it commanded full deflection of the SRB nozzles and Vulcan, causing the vehicle to rapidly pitch over 37 seconds after launch. Not designed to survive such an angle of attack, the forward end of the vehicle succumbed to the high aerodynamic forces, or in other words, the front fell off. Shortly after, with it being very clear that the current trajectory had departed from the intended trajectory, the flight termination system was triggered, causing debris to fall down into the Amazon rainforest below. The reason for the flight termination system being triggered, despite the fact that the vehicle was already breaking itself apart, definitely seems to fall into the smaller bits are better than bigger bits of debris rule discussed earlier. There also could have been a similar situation to the Challenger disaster had the FTS not been triggered right away. Looping the initial pitch over, the SRBs keep firing without issue. Had the Ariane first stage been compromised, the SRBs could have detached and continued flying on their own. One difference between the Challenger disaster and this maiden flight of the Ariane 5 though was the type of flight termination system being flown. On STS-51L, the SRBs were terminated by the range safety officer. Ariane Flight V88, on the other hand, was using an automated flight termination system. By triggering the AFTS right away, the entire vehicle was neutralized. For our next example, we move to the Wallops Flight Facility in Virginia, where in 2014, Orbital Sciences Corporation was conducting the 5th flight of its Antares launch vehicle, launching what was to be the 3rd operational Cygnus resupply mission to the International Space Station. However, as we're about to see, it didn't make it that far. 15 seconds into flight, there was an explosion in the liquid oxygen turbopump within one of the 2 AJ-26 main engines, specifically Engine 1, due to some components within its hydraulic balance assembly seal package not being properly aligned, causing contact and frictional rubbing between rotating and stationary components, which led to a fire, which led to an explosion. Said explosion then damaged Engine 2, resulting in a total loss of thrust from the first stage, causing Antares to start plummeting back to Earth. Just prior to its impact with the ground, the range safety officer issued the termination command. Whether this made much of a difference to the imminent huge explosion, I don't know, but according to NASA's independent review, Antares was terminated to, quote, minimize the potential damage from the expected ground impact and ensuing explosion of the vehicle. As that language shows, this flight was terminated with a manual flight termination system. NASA's report also goes on to acknowledge the damage to the launch pad and surrounding ground support equipment, and from this aerial photo, you can certainly see how toasty it got around the impact point. But all things considered, Orbital were pretty lucky that the rocket itself didn't fall directly back onto the launch pad. By the way, if you're a newer space fan and you have no idea who this Orbital Sciences Corporation is, they shortly renamed to Orbital ATK following a merger, and were renamed again 3 years later to Northrop Grumman Innovation Systems following a purchase by, you guessed it, Northrop Grumman. A couple of years after that, Northrop Grumman Innovation Systems was merged into the rest of Northrop's operations, which is why today Antares, Pegasus and Cygnus are all operated by just Northrop Grumman. Fun fact, the Antares 130's engines were originally designed for the Soviet Union's N-1 moon rocket. When that program was ended, literally dozens of these were left in storage, 36 of which were sold to Aerojet in the 90s. Originally known as the NK-33, following refurbishment, they were redesignated as the AJ-26. Next, we're headed back to the 90s, specifically the start of 1997, when McDonnell Douglas attempted to launch the first Block 2R GPS satellite aboard their mighty Delta II, launching out of Space Launch Complex 17A at the Cape Canaveral Air Force Station as it was then known. Just like Orb 3, this flight was a short one. At T+6 seconds, a crack started to form in the number 2 GEM 40 solid rocket motor, a motor developed by Hercules. This crack continued to widen over the following 6 seconds, as the Delta II continued to blast uphill. Come T+12 seconds though, the composite casing was compromised to the degree that it ruptured, flinging debris at the neighbouring number 8 motor, which then also failed. With the start of this chain reaction of motors knocking each other offline, the first stage and remaining SRMs were automatically terminated by its onboard computer, causing what is, quite frankly, one of the most spectacular rocket failures of all time. Note how I only mentioned the first stage and solid rocket motors though. The other stages were ejected, and while not ignited, once again it appears as if the smaller bits are better than bigger bits of debris rule came into effect, as at T+21 seconds, the range safety officer manually ordered the destruct command of those stages. But wait, didn't I just say that the rocket was automatically terminated? Well, in the case of these older rockets, these termination systems were limited in their abilities. Basically, if something catastrophic had already happened, then that was pretty easy to detect using 90s technology. Therefore, the primary method of triggering the flight termination system remained with the range safety officer, the human in the loop. We'll talk about these older systems more in a second. You may also be wondering whether the payload is super duper secret rule also came into thought when terminating the upper stages, and well, even if it did, the payload fairing and GPS satellite inside survived intact until they impacted the ground. GEM's solid rocket failure may also be ringing some bells. There's a 50% chance you've seen one fail if you've watched a launch of United Launch Alliance's Vulcan rocket, as of the time of publication. After being manufactured by Hercules in 1995, the graphite epoxy motor family was handed over to Alliant Tech Systems for 20 years before ending up at Orbital ATK. Blah blah blah, they're now Northrop Grumman, with the GEM 63 and GEM 63 XL actively in service on the Atlas V and Vulcan respectively. Spectacular explosions aren't limited to orbital launch attempts. Suborbital flights can also go equally wrong. One example is the final flight of the F9R Dev-1, a development vehicle used by SpaceX to prepare for landing Falcon 9 boosters supporting orbital missions. Nowadays, it is an incredibly reliable system. In 2014, not so much. Following on from their successful Grasshopper test program, which still stands to this day as an excellent display piece, the McGregor test site in Texas was next host to 4 successful flights of the F9R Dev-1, reaching altitudes of up to 1,000 meters, testing technologies such as the newly stretched Falcon 9 V1.1 tanks, landing legs and steerable grid fins. Come its 5th flight though, things went a little bit sideways, quite literally. Anomalous sensor data caused the rocket to deviate from its nominal trajectory, and after rotating over 90 degrees with the rocket pitching down, the automated flight termination system triggered, neutralizing the vehicle. I think this also falls under the smaller bits are better than bigger bits of debris rule, considering the McGregor test site's proximity to the city of McGregor, which some 5,000 people call home. While a failure, this suborbital hop did make some history of its own. It was the first triggering of a modern automated flight termination system in the US, and it certainly won't be the last. The next FTS example comes from another American rocket, this time the maiden flight of Firefly Aerospace's Alpha Block 1. It was recently upgraded with an automated flight termination system, but back in 2021 it was flying with a manual FTS. After igniting its 4 Reaver engines and clearing the pad at Space Launch Complex 2 West in Vandenberg, Alpha started climbing, but at T+15 seconds, engine 2 was lost. It wasn't an eventful explosion thankfully, but instead the propellant main valves just closed, leading to a 25% reduction in thrust. While subsonic, the remaining 3 engines had enough authority to keep Alpha stable, but when entering the transonic regime, that was not the case. Reaching the speed of sound at T+2 minutes and 20 seconds, the vehicle tumbled out of control shortly after. After 10 seconds, it was pretty clear that the rocket wasn't going to make it, leading to the range safety officer at Space Launch Delta 30, which manages the Western Range, to send the destruction command. A year later, Alpha's second flight was able to achieve orbit, although the educational payloads on board were deployed into a lower orbit than expected. To date, the vehicle has flown 7 times overall, with a 57.1% success rate and a brand new Block 2 variant on the way. Enough of the modern rockets, let's take a look at a couple more vintage failures. First, Martin Marietta's Titan 34D. Derived from the Titan III, this variant saw 2 failures, one in 1985, the other in '86. It's the latter one that we'll be focusing on. Aboard the rocket was Keyhole 920, the last Keyhole 9 in a series of photographic reconnaissance satellites built for the National Reconnaissance Office. Also launching from Vandenberg, KH920 departed Slick 4 East, the same pad used in the modern day by SpaceX, but shortly into flight, at T+8 seconds, the right-hand, or number 2, solid rocket booster ruptured. These motors were designed so that the solid propellant inside touches the metal casing, but for this specific motor, something in the process had not gone to plan, as an air pocket remained between the propellant and the casing. The exact reason for this air pocket was never found, but the investigation did report that the manufacturer, United Technologies, had inadequate quality control measures. Due to the government's priority with the Space Shuttle program, expendable vehicles like Titan were flying less often, and the contractors which built them had been cutting costs to prepare to wind down the programs entirely. That government priority soon shifted following the Challenger disaster, but that's a topic for another video. Regardless, this cavity was all it took to allow hot exhaust gases to burn through the casing, causing the SRB to rupture. Just like the Delta II failure discussed earlier, the Titan 34D was designed with a rudimentary automatic termination system for the first stage and solid boosters, and by rudimentary, I mean physical lanyards were hooked up to each booster. This was called the inadvertent separation destruct system, named as such because should a booster separate inadvertently, the lanyards would break, closing an electrical circuit which would unzip the motor, causing its flight to be terminated. When the right SRB ruptured, it caused the vehicle to shift in such a way that the resulting torque caused the left SRB to break away. This action then triggered that rudimentary termination system, blowing up the first stage. But during that entire fiasco, when the right SRB ruptured, it actually damaged the AFTS lanyards. That meant when it broke away, it was still in one piece. It didn't terminate, and it flew back to the ground largely in one piece, and those boosters certainly weren't small. Notice how again I didn't mention the upper stages? Well, that's because, just as with the Delta II failure, they were also ejected away from the explosion of Stage 1. They were later terminated manually by the range safety officer at T+20 seconds, or 12 seconds after the initial failure. At the same time, the KH-9 was destroyed, not because of the terminated stages, but because of its own internal self-destruct mechanism. Remember the super-duper secret payload destruct rule from earlier? Yeah, that probably came into effect here, especially during the Cold War. Almost a decade and a half later, in 1998, the final generation of the Titan family, the Titan IV, also experienced an interesting encounter with its Flight Termination System. Launching out of Space Launch Complex 41 in Florida, the NROL-7 mission was attempting to send a Mercury Communications intelligence satellite into orbit. It did make it a bit further than the previous example, but definitely nowhere near space. At T+39 seconds into flight, the Titan IV experienced an electrical short, which caused a momentary electrical power drop to the guidance computer. That's really bad. How does something like that even happen in the first place? Well, the post-flight investigation identified that dozens of wires inside the Lockheed Martin manufactured first stage were either damaged or chafed. The fuselage featured a number of sharp metal protrusions, which made it incredibly difficult to near impossible to install or replace wiring without it getting damaged. Add extreme pressure from the United States Air Force to meet deadlines, and quality control was very poor. Anyways, back to the Titan. Following the electrical short, power was restored to the guidance computer. That must be good, right? The rocket can steer itself again? Well, unfortunately not. When it returned online, the computer sent an unfound command it didn't have any reason to send. Pitch down and you're right. As you'd expect, the Titan IV wasn't designed to survive such a maneuver at near supersonic speeds. 1 second after the electrical short, the aerodynamic forces ripped away one of the solid rocket boosters. And unlike the Titan 34D failure 13 years prior, this one did activate the inadvertent separation destruct system. This unzipped the booster and took the rest of the rocket with it. 5 seconds later, the range safety officer manually triggered the flight termination system to ensure that any larger pieces of hypergolic debris were turned into slightly smaller pieces of hypergolic debris. Although unfortunate for the payload, this launch is a great example of the older days of automated termination systems. There was no computer on board. When a physical connection between the first stage and one of the solid boosters was broken, the electrical circuit was complete and the SRB was terminated. This is also a great example as to why flight termination systems require their own redundant power supply. The main electrical power on this Titan IV literally went out for a split second, to the degree that the guidance computer, arguably the most important computer a rocket has, turned off. I think it's safe to say that the Titan program hit a rough patch during this time period. Following this launch failure, the Titan IV saw 2 more consecutive failures, but neither of these required the use of the flight termination system, so they're outside the scope of this video. The vast majority of rockets launched today make it safely to orbit, meaning they don't have to make use of their FTS. But that being said, when a rocket reaches the safety of orbit, how do you actually turn it off? If you've watched any launch broadcast over the past few years, there's a good chance you've heard the phrase "stage number FTS has been saved."
Stage 2 FTS safe.
This call out from mission control indicates that the FTS on that stage is now inhibited. Even if a terminate command is sent, it won't trigger because the termination system has been blocked off from receiving those commands. This interruption can either be electronic or mechanical, meaning either the software is blocking the FTS or a mechanical component has physically disconnected the FTS. But in the case of stage 2, it's still flying. Why is the FTS inhibited? Well, when a stage reaches orbit, a decision has to be made as to the least worst outcome. If something were to go wrong with the second stage at that point in flight, it and the payload are very likely to entirely burn up come re-entry into the atmosphere. In the case of Falcon 9, these parts of the rocket are designed to disintegrate, with debris very rarely making it through. If there was a problem after the stage had reached orbit and the flight termination system was triggered, what would happen? Well, if it uses an explosive FTS, it would explode the stage and payload into hundreds, thousands, perhaps even millions of tiny pieces of space debris now whizzing around the planet at 27,000 kilometers an hour, which could potentially strike other satellites or even spacecraft. Not good. Therefore, in this specific scenario, not using FTS is the best option. A similar procedure is used when it comes to first stage recovery with the Falcon 9. Just before landing, its FTS is saved, preventing it from exploding should something go wrong. This is because, as has been demonstrated with a few boosters at this point, should something go wrong, it will be plunging into the ocean momentarily anyways, and I'm sure SpaceX would prefer to avoid sprinkling Falcon 9 parts all over their drone ship if it can be avoided. That being said, however, the periods of flight when the flight termination system is disarmed need to be very carefully selected. Why do I say that? Well, let's take a look at the infamous 2013 failure of the Proton M. Launching out of Baikonur, the vehicle started swaying back and forth shortly after liftoff. The reason why was later found out to be a number of critical angular velocity sensors installed upside down. Talk about quality control. Because these sensors were upside down, the rocket thought it was upside down and therefore tried to correct it. Proton, however, is not designed to flip 180 degrees in flight though, meaning soon enough, its structures were compromised, causing the vehicle to split apart and impact the ground shortly after. Notice, however, that none of these explosions were caused by the flight termination system. Surely after seeing a vehicle rotating out of control it would have been activated, right? In this specific case, the flight termination system was the engine cut-off type, much like ESA Aerospace's Spectrum rocket, which we were talking about earlier. This engine cut-off was inhibited for the first 42 seconds of flight, and since this failure happened well within that period, there was simply no way to terminate the flight. Well, there you have it. Hopefully this has explained what a flight termination system actually is, why they're needed, and how they actually work. It's not a magical box full of explosives. Sometimes it just cuts off the engines, and sometimes it's not a box at all, but instead a team of people on the ground manually keeping an eye on the vehicle's performance. I've been Ryan Caton for NSF, thanks for watching, and goodbye.